Okay, so let's talk about 6.3. This is the fundamental theorem of calculus. So I'm going to abbreviate it as FTOC. You might also see it abbreviated as just FTC, all right? So basically we have done limits, derivatives, indefinite integrals, and definite integrals. And those are all the major topics. When we've done definite integrals, we've done some rules and we used signed areas to evaluate them. What the fundamental theorem of calculus does is it takes away that whole graph idea and it moves it back to the algebraic rules, okay, for the definite integrals. So we don't have to worry about if the area was above or below. The fundamental theorem, it takes all of that away. So basically, I'm going to draw a little, this is an informal proof. I would like to visually show you what a rule is doing to help you get a better understanding. Actually, let's make some of this above. All right, so let's just say we had a curve and it went like this. Okay, we want to go from A to B. So we might have some above, some below. It doesn't actually matter for the rule. So what the fundamental theorem of calculus does is it says, hey, what if we integrate all the way from 0 to B, and I find all of that area, and then I take off from 0 to A. Well, if that happens, then I would just be left mathematically with the overall net area from A to B. And that's kind of the principle behind this rule. So when we go to do our integral, if we integrate and we have our limits A to B of a function, which is the derivative, then it's going to, the integral is going to equal the original function, big F, and we change our notation and we put our limits at the end with this bracket. So that denotes that we have integrated, but we haven't substituted those values. When we do the substitution, we're going to substitute our upper limit, B, into the function and subtract when we substitute our lower function, because that's the idea. If we integrate all the way up to B and find the total area, then we integrate from 0 to A and we subtract those, we'll just be left with the overall area from A to B. Okay? So you will not have to do opposite signs or anything like that. Even if these limits are not in order, as long as you keep them in the same upper and lower values, mathematically it will work itself out. Okay? So I don't formally prove it, but if you Google it, they go through this a lot more formally than what I just did. So let's look at example 1. Whenever you do these functions, you're going to first notice that my limits are 0 and 9, and so I've got this as a power. So I want to integrate with the power rule. So U substitution will still work, the power rule, all the trig, natural log, E integrals as well. We're just going to mix them all up. So I integrate, I'm going to add 1. So 3/2, divide by it, which means multiply by the reciprocal. And then I integrated, but I haven't done my limits. So we always put the limits on the right side with that bracket. So then what happens is I'm going to substitute 9. So I really do just write 2/3 times 9 to the 3/2 minus, and then we plug in the 0. Some students skip this step. I just think it's good to write it all out just in case you make a minor error. Now, this would be a non-calculator question. So as a review, remember the top number is the power, the bottom number is the root. So you always want to do the root first. So the square root of 9 is 3. 3 cubed is 27. Okay, so 2/3 times 27, well, that goes in 9 times. So 9 times 2 is 18. Same thing here. 0 to any power is 0. So we get, if you want to change this into a common denominator, you definitely could. So 54 minus 2 is 52/3. Or 17 1/3. It's really a choice. This would be multiple choice. That's it. So graphically, if this is the square root, what we're really doing is we're saying from 0 to 9, which the square root of 9 is 3, we're adding up that area. That's really what we're doing, okay? And so that exact area, because it's all above the x-axis, is 17 1/3 units. That's what we're doing here, okay? We are doing area, it's just we're doing the algebraic strategies because of time. It's quicker. And this is a curved region. We wouldn't be able to do this geometrically. Does that make sense? So this is the exact area under the curve between the x-axis from 0 to x equals 9. Okay? I really do like to make the connections so you know, like, oh, I found the integral, but I really have no idea what that is. You found the exact area. If some of this was above and below, that's why I said net area, because it is going to take those signed area values into consideration. Okay? All right, let's try the next one. So first thing I want to do, though, is rewrite this part. So I'm going to write that as 2/3 and then x to the -2. So when I integrate, we're going to get 2/3, add 1, divide by it, and we're going from 10 to 5. So I'm going to rewrite this nicer. I've got -2/3x from 10 to 5. So then we're going to plug in 10. So -2/30 minus, remember, we always subtract, -2/15. So we get 2 negatives, make a positive. This is really 4/30. So -2 plus 4 is 2/30, which is 1/15. Okay. All right, the next one. Remember, when you're adding, we can integrate these separately. Now, you don't have to. I actually don't do this separately, but if you want to, you're welcome to, and then you just have one final answer. So I'm going to go ahead and erase this, and I'm going to do it all together. So when we integrate, this one's going to be a power rule. So 4, I'm going to add a power of x and divide by it. And then I have to think, well, what trig function had a derivative of secant? Well, that was tangent. And we're going from pi/4 to 0. Now, the important thing is if you don't separate the two functions, that you use parentheses. So this is really when I plug in pi/4, and this I'm going to subtract off the entire thing when I plug in 0. So let's reduce this. I get 2x squared. So I have 2, and then I'm plugging in x, which is pi/4 squared, plus the tangent of pi/4. And we'll worry about that in a minute. Minus, I want to put in parentheses if I plug in 0. So I would have 0 plus the tangent of 0. Now, I don't know if we've done tangent for a while. So you're going to have to remember tangent has an asymptote at pi/2 and negative pi/2. And so the tangent of 0 is 0. If I clean this up, I get 2 pi squared over 16. Plus, I need the tangent of pi/4. Well, that really, I'm going to write it up here, is the tangent of 45 degrees. So if we draw that 45-degree triangle, I get 1, 1, √2. So tangent is opposite over adjacent. So opposite is 1, adjacent is 1. So the tangent of pi/4 is 1. And all of that's 0. So watch your signs, watch your substitution. There's a lot. This would reduce, so we would get pi squared over 8 plus 1. Okay, I like to keep them all together using the parentheses. So same thing with number 4. On number 4, I really could integrate them all separately, have my limits each time, but it's quicker if you just do it all at once. So we will go ahead and integrate. I'm going to add a power. So I get 3x cubed divided by 3 minus 2 add a power minus 1 add a power. And see, now that we have these limits, I forgot to even mention that, we don't have that constant of integration, because basically when I would have added it and subtracted it, they would cancel each other out. So with definite integrals, there is no plus c. I definitely should have said that a lot earlier. So technically, we're going to do f of 3 into all of 3 parts minus f of negative 1. So those reduce, and I don't need that. So I like to draw big parentheses. So if I plug in 3, I get 27 minus 3 squared minus another 3. If I plug in negative 1 cubed minus negative 1 squared is 1 minus another negative 1. So what's that? 27 minus 12 is 15 minus 2 negatives make a positive. So those cancel and I get negative 1. So 15 minus negative 1 is 16. That would be my overall net area. I don't know if it's positive or negative y values on the original function. So, all right, example 5, I always like to throw in here. We did this with, I think 6.1, but absolute value. Now, if I want to do absolute value, there is a way that we can do this algebraically, but we have to find out where our vertex is, and then we have to split it up into 2 integrals. Well, that's very time consuming. So I will do that after I show you my recommended way. I would say make the graph and then use the areas. Use signed, sorry. Still. So even though I know the fundamental theorem of calculus, I don't use it for absolute value functions, okay? Now, sometimes if this was a different curve, like if this wasn't 4 minus 2x and this was squared, I would show you how to do it. So that's why I am going to show you the different technique. So on this, if you want to find where the vertex is, you can set that equal to 0. So add 2x, divide by 2. So at 2, 5, I'm going to have a vertex. And then we just make a table of values. If I plug in 0, I get 4, 2, 3, 4. Plug in 1, I get 2. So I know that's a line. I know it's terrible. Plug in 5, so 4 minus 10 is negative 6, but it's positive, so that's at 6. Okay, so I've got 1/2 base times height plus 1/2 base times height. So this base is 2. The height was 1, 2, 3, 4. So half of 8 is 4. This base, 1, 2, 3. The height was 6. So half of 18 is 9. So our overall integral value is 13. Okay. Now, let's say this is not just a line. Let's say it was something squared. We wouldn't be able to use geometric areas. So I do want to show you the other strategy. So I know the answer is 13, but we are going to go ahead and get rid of all of that. Okay, so now what we do need to do is we need to find out where the inside graph would cross the axis, because what this absolute value does is it makes all the y values positive. So you would just sketch the original curve, no matter what it is. So if we had 4 minus 2x, I would have a line up at 4, and I would have a slope of negative 2x, basically, okay? And so what it does is it takes all of this and it bounces it up. So then that's not there anymore. So I need to find out where it actually crossed the axis. So we would still set this equal to 0, and we found that it's 2. So mathematically, what we want to do is we want to go from 0 to 2. And since I didn't have to change the sign on the first part, because that was where my line was, that's going to stay the same. Okay? My part from 2 to 5, that originally, when I ignored the absolute value bars, that was under the y-axis because we had negative y values. And so what I really want to do is I want to take the opposite of this. So from 2 to 5, we really need to take the opposite of these values if I remove that absolute value sign. Okay, so you'll need to figure out which part of your, whatever shape it is, needed to be reflected. Okay, so then we got to do all the math. So I would add a power of x, add a power of x and divide by it, and we're going to go from 2 to 0. Now this minus, I can go ahead and factor out, so we'll subtract off, and then I'm going to put like a little bracket here. So I'm going to add a power of x, add a power of x and divide by it. From 5 to 2. Okay. I know there's lots of options. I could have distributed the negative, kept it as a plus. There's lots of things to do. So remember, this is f of 2 minus f of 0. So if we plug in f of 2, so I get 8 minus 4, 0 minus 0. So we're going to get 4. Minus, and then we're going to do all of this. I like to keep this all together. So this is really f of 5 minus f of 2. So if I plug in 5, I get 20 minus 25. Let's make this bigger. There we go. And then if we plug in 2, so I get 8 minus 2 squared is 4. So we get 20 minus 25 minus 8 minus 4. So I would get negative 9. So then 4 minus negative 9 is 13. Okay. Now, there's even other ways I could have integrated that by distributing the negative, but notice mathematically it all does work out. So you can decide if it is just a linear absolute value to do that. Okay. Let's look at your assignment for a second. I know I gave you one absolute value. Oh, no, I didn't. So I will be throwing in an absolute value later on. Okay, let's look at example number 6. So on number 6, I'm getting a graphing calculator, but when you go to do your integrals, we can use a graphing calculator. So I do want you to know how to do this so you can check your answers, okay? So when you graph it on your calculator, you'll do it just like your derivative, but you'll just use number 7 instead of number 6. So in y1, you are going to put in the derivative, okay? And then when you do your second calc for the trace, go to second trace, which is really calculate. You're going to go, I think it's number 7, and it'll say integrate. I know, I'm getting it because I got a grant for it, but I just don't have it yet. So what I want to do is I've got my own calculator. Yeah, and I can't do this on it. But when you type this into your screen, I'm going to go to Y1. And for now, I'm just going to have to describe it. I'll remake this video probably in about a month when I get my software. But put in cosine x, and I know you can't see me doing anything. I'm going to make sure that I'm in radians. Okay, and then I'm going to go to my graph. So then we're going to go to second, calculate, and we're going to do number 7. So number 7, it has f of x dx. So you'll hit enter. And then it says lower limits. So I want the lower limit to be 0. If that wasn't already my screen, you could type in the number. So I'm going to just hit 0 and say enter. My upper limit, I want to use pi. Don't say 3.14. Use the pi button, which is on the right side. So I'm going to say the blue pi, which is under clear. And then notice it says this. So it says negative 3.21 e to the negative 14. Okay, and so some students will write that. Now, because of an approximation program that your graphing calculator uses, it has this default. Hopefully you've seen this before, but if not, we're going to talk about it now. This E is really scientific notation. So this means negative 3.21 times 10 to the negative 14. And so what that negative does is, remember, it moves this decimal 14 places to the left. So it's all of these zeros, and it's negative. 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so it says, oh, well, that's really close to 0 because it's supposed to be 0. But it's using something called Riemann approximations, which is unit 7, to actually calculate your areas. So if it's off a little bit, it's going to be to 3 decimal accuracy, so the AP is fine. But you need to understand, anytime you see an E, you really need to write 0. Okay, so you are welcome to type in these integrals, and you can evaluate the limits if you want to check your answers. Okay, but you don't want to do them just to do the integrals. So it would just be for checking. All of these should be done by hand. All right, so I have given you 7 problems to try, and good luck.